Hello everyone, and thank you for joining this session. In this session, we're going to be looking at some of the details of Eigrp. Eigrp has three main tables that it populates. It populates the neighbors table, the topology table, and also the routing table. So we'll be looking at these three tables. I've also listed some of the commands that we're going to be using throughout this session, and also some of the terms that I'm going to be referring to during the session. In our lab today, we have 5 different routers. Each router is configured with Eigrp and is also configured with autonomous system number 10. Also configure a loopback on each one of these routers. For example, router 1 has 10.0.0.1, router 2 is 10.0.0.2. So the very last octet represents the router. So router 1, 2, 3, 4, and 5. The only commands that I've configured so far to enable Eigrp are these 2 commands. The router Eigrp 10 for process 10, and the network command with 10.0.0.0/8. And this is so that we can enable Eigrp on all of our interfaces. And so these are the 2 commands that I have configured on each one of my routers. So you can see here, that's all we have configured. When working with routing protocols, the command that I usually like to run first to kind of get an idea of what's configured on our router is show IP protocols. When you run this command on any router, it will give you a list of all the processes, all the routing processes that are running in the router. In this particular case, or in our lab, we're only going to be focusing on Eigrp, so we only have Eigrp 10 configured. This is a very helpful command because it gives you a lot of the default values and a lot of the settings that are configured. So the first important one is the metric weights. So Eigrp has 5 different metrics that it can use to calculate its composite metric. Each one of these K values represents something different. And so when it has a 1, it means that K value 1 is going to be used as part of the metric. K value 2 equals 0 means that K value 2 is not going to be considered, when it's calculating its metric. And so it has 5 values to choose from, but by default, it only uses K value 1 and also K value 3. And so these K values, they have different meanings. And so here we can see that K value 1 is bandwidth, K value 2 is load, so it's not going to use load. K value 3 is delay, so it's going to use delay. And K value 4 is reliability, so it's not going to use K value 4. And K value 5 equals 0, so that's not going to be used either, which is the MTU. So by default, Eigrp would use K value 1 and K value 3, which is bandwidth and delay, to calculate its metric. And so it's important to know these K values, and here's a quick reference of what each one of them what they are. The next section we're going to look at is the topology section here. So there's quite a few items here. The first one is the active timer, and it's set to 3 minutes. This particular active timer refers to the stuck in active timer. And stuck in active is kind of a scenario that a router may run into when it's trying to refresh its routing table. So say for example, if router 1 is trying to determine if router 2 has a route to router 3. So the way this operates is router 1 will send a query to router 2 checking to see if it has a route to router 3, but router 2 may not have a route, and so it sends a query to router 3, and router 3 may be having some problems. Router 3 may be having some sort of hardware issue or high CPU, whatever the case may be. Router 3 is busy, so it doesn't have time to send a response back to router 2. And since router 2 doesn't get a response, it doesn't send a response to router 1, and so router 1 is just waiting for that response from router 2, but router 2 is waiting a response from router 3, and so this is where you get that situation where router 1 is just kind of stuck and active. And so the default timer is set to 3 minutes. So that's kind of the default value that ERGRP sets that to. The next item here is the distance. This particular distance refers to the administrative distance. So in any sort of routing protocol, every route has some sort of administrative distance assigned to it. So by default, internal ERGRP routes are assigned the value of 90, and any external routes are assigned 170. And so this is the default value for the default administrative distance for internal routes and external routes for ERGRP. The next value here is maximum paths. So maximum paths in this particular section, it refers to the number of equal cost paths, or ECMP. So ECMP, equal cost multipath, is the way this is referred to. And equal cost multipath is basically the number of routes that ERGRP will insert into the routing table by default. So to explain equal cost multipath is like, for example, if router 1 is trying to get to router 3, router 1 can go to router 2 and then down to router 3 to get to this loopback interface. Router 1 can also go to router 4 and down to router 3 to get to the same loopback. So in this case, it has 2 routes. So this cost here and this cost, if the cost is the same, so if this is gigabit, gigabit, and gigabit and gigabit, it's basically the exact same distance. It will insert this route and will also insert this second route into its routing table, and so now it will insert both routes. So by default, it can insert up to 4. So if there was another route to get to router 3, say for example there was another router here, now there's another path here, so now that's 3. So 4 is not the maximum path that it can configure. You can actually update that value from 4 to 6. So but just ERGRP by default sets it to 4. The next value here is maximum hop counts. So ERGRP keeps track of how many hops each route, or how many hops it takes to get to a specific route. So in our lab here, say for example, to get to router 5 here, is going to count 1 hop. It's going to count 2 hops. So it's 2 hops to get here. This direction is 1 hop, 2 hops, and then 3 hops. So it keeps track of how many hops it takes to get to the destination. And so by default, ERGRP has the value set to 100. So anything that's more than 100 hops is just going to discard it. And this is not necessarily the max that ERGRP will support. It's just the default value that it's set to. by default it can support up to 224. The maximum metric variance value in this case by default is 1. And so we'll be looking at this particular value in more in detail here in a few minutes. The information here below, this particular routing for networks, this basically refers to the information that we have provided Eigrp when we configure the network command. So if we were to have other networks here, they would show up in this particular section. Routing information sources. This refers to the sources that it's learning routes from. So in this case, because there's two neighbors, it's learning routes from these two neighbors. In this particular case, 10.1.2.2 refers to router 2, and 10.1.4.2 is referring to router 4. So Eigrp neighbors, we can see that it has two neighbors. If we look at this next command, this output from this command, neighbors, show IP Eigrp neighbors, it gives us a little bit more details about our neighbors. Here it tells us that this particular neighbor was learned or was discovered through gigabit 00, and this particular neighbor was discovered through gigabit 01, which are our two interfaces here on router 1. It also has the hold timer, and this is kind of a countdown. The hold timer by default is 15. If you're interested in trying to determine what's the configured hold timer for a particular neighbor, you can run the command show IP Eigrp interface detail, and you can set the interface, for example in this case 00 gigabit 00. For this particular neighbor, the hold timer is 15 and the hello interval is set to 5. It's important to know how to find these values so that if you're troubleshooting an issue and your neighbor keeps bouncing, it's possible that it's reaching the hold timer value, and this is where it tells you what it's set to. The uptime is self-explanatory. The soft round trip time is important to keep in mind. The soft round trip time basically is a time in milliseconds, and this is basically the amount of time that the router is experiencing or is waiting for a reply from the neighbor. So basically the round trip time is this router here sending a message to this router and this router replying it back. And so this should normally be a pretty low value. In this case, in our lab, we can see that it's 12 milliseconds. If this value increases significantly, if it goes up to the thousands, you know that there's a problem possibly somewhere in here between these two routers. And the round trip timeout value is basically saying if I don't receive a response from my neighbor within 100 milliseconds, it's just going to say, okay, that neighbor's down. So that's also kind of one of those hold timers, kind of saying this is a timeout value. If this goes over 100, then it's considered that the neighbor is not responding, is having trouble. The next section here about the queue counts. The queue counts is basically refers to the number of packets that are in a queue, and so if this count starts incrementing, it basically also indicates that there's a problem with the neighbor. So these values here, SRTT and SRTO and queue counts, are all good values to look at when there's a network issue. Okay, so now that we've looked at this output of show IP Eigrp neighbors, Let's go and look at our topology table. When looking at the topology table, there's actually two commands that you want to be familiar with. One of them is the show IP ERGRP topology command, and the other one is show IP ERGRP topology all links. And so these two commands reference the same database, the same table. The only difference is that when you run show IP ERGRP topology, it's only going to show you the routes that are considered successors and the routes that are considered feasible successors. And so those are two of the terms that we're going to be looking at and discussing as well. Whenever you run the command show IP ERG topology links, it actually shows all the routes, including the successors and feasible successors and any other routes that it knows to get to a specific destination. For example, when we run the show IP ERGRP topology command, for example, for this particular destination, we only see this route. But whenever we run the command with the all links, we can see that for this same route, we have actually two. For this destination, we have two routes. And so that's the difference between these two commands. To understand the output of the show IP ERGRP topology, we'll have to take a step back and really understand what these values are here. So as you can see, every route has these two values in parentheses, and this is what is considered a composite metric. And so the composite metric is composed of two values. The first value is considered the feasible distance, which you can see here, FD is 3072. That's the feasible distance. And then the second value is considered the reported distance or advertised distance. You may see in some literature refer this second value as reported distance, or sometimes you may see it as referred as advertised distance. And so the way these two values are calculated is ERGRP uses a formula called the dual formula. And so we won't get into the formula itself because it's very complex, but we will look at these values that it calculated. So the very first value here, the feasible distance. The feasible distance is calculated by the router, and the reported distance is actually received by the neighbor. So whenever a route is sent from router 1 to router 2, router 1 will send the reported distance, which is this particular value here, and whenever router 2 receives the reported distance, it will calculate its own metric, and that becomes the feasible distance. So these two values here are two different metrics from two different perspectives. So in order to get to this particular route or destination, router 1 says that my metric to get to that particular destination is 3072. But from this particular router's perspective, gigabit 01, which would be router 4, is 2816. That's the reported distance. So ERGRP keeps track of both of these metrics. And so in the show IP ERGRP topology output, it's only going to have the successors and feasible successors. To really understand how these routes entries come into play, there's some rules that you have to abide by. For example, only the successors will be imported into the routing table. So say for example, in this first route here, 10.1.4.2 has one successor, and so this means that this particular entry here will be inserted into the routing table. So if I do show IP route and I go to this route here, the very first entry in our topology table is a route to 10.4.5.0/30. The exit interface is gigabit 01. It's inserted into the routing table and is known via ERGRP10. In this case here, we have two successors. So two successors, we can see that the feasible distance and also the reported distance are the same for both. So this is 10.1.2.2 and 10.1.4.2. So in order to get to 10.0.0.3, there's two routes, and because they have the same composite metric, they are both going to be successors, and they're both going to be inserted into the routing table. So we can take a look at the routing table for this particular network here. And we can see that we have two routes. One is going to exit via gigabit 01, and the other one's going to exit via gigabit 02. Now that we've kind of looked at both of these values, what I like to focus on is router 5, so that I can kind of explain how these values can be manipulated. So in order to get to router 5, when we look at the ERGRP topology table, we can see that it only has one specific successor, but there's actually more than one route to get to 10.0.0.5 from router 1's perspective. And so in order to view the second route, we need to run the command all links. And so here we can see that there's actually two paths to get to the 10.0.0.1/32 subnet. So the reason why only one entry is shown as the reason why we only have one entry in this particular output is because in order for a route to be considered a feasible successor, it has to meet the condition that this particular value here, the feasible distance, must be higher than the reported distance. So in this case, because they're both the same, it doesn't qualify to become a feasible successor. So there's only one successor. But say, for example, if we wanted to make this route a feasible successor, the only way for us to do that is to be able to increase this value, the feasible distance, increase it so that it's higher than this value. And so EIGRP gives us the ability to do that. And so what we can do is we can create an access list that matches this particular address, and then we can use the command to increase this value by, let's say, 10 and make it 131082, and then in that case this value will be higher than this value, and then now it can be considered a feasible successor. So let's take a look at that. So I can create this ACL, IP access list 1, and we can make it to permit 10.00.5. And so we can go into our configuration, we'll use the offset list, and our access list is 1, and then we want to influence the inbound updates, and we want to offset it by 10, and then we want to specify the interface, and so in this case gigabit 01. So gigabit 01 is the current successor, so we want to influence this value by 10, and so we're going to specify this interface, gigabit 01. So by doing that, now if we go to if we run the same command here, show IP EIGRP topology all links, we get this notification here that feasible, that there was a change with EIGRP, and when we look at this particular route, we can see that now it's 131082, which is higher than 131072. So if we run the show IP EIGRP topology command, we should be seeing a second route here, and in this, because this is a virtual lab environment, sometimes you have to restart the process to take effect. Clear IP EIGRP autonomous system 10 neighbors. We're just going to clear all the neighbors. Let's run the command again. And now we can see that we have a successor, one successor, and one feasible successor. So this is a feasible successor now. We only have one successor, but we have a feasible successor now. And so what this allows us, what this provides us, is a secondary route in case we lose the first route. So when we first started, the topology table only had a route this way as a successor, and it didn't, even though there was a route this direction, it wasn't considering it as a feasible successor or as a backup route. And so what we've done is we manipulated the metric so that this particular route can qualify to become a feasible successor. And the only way that it can qualify to become a feasible successor is for that the reported distance has to be lower than the feasible distance. And so that's what we did here. We increased the feasible distance to be higher than the reported distance. And now we can see that we have a successor and a feasible successor here. Now, just because it's in the topology table doesn't necessarily mean that it inserted into the routing table. So if we go back to the routing table and we search for this particular route, we still only have one route. But Eigrp now has in this topology table a successor and a feasible successor. And so now if we were to lose this particular route, it will immediately insert this second route into the routing table and not have to run through its whole calculations to find, okay, what other route can become a successor, because now we have configured it so that this is the successor and now this is the feasible successor. The last command that I want to go over is called the variance command. And so we saw that at the very beginning with the show IP protocols command, which is here, the maximum metric variance is equal to 1. So if we ever had a situation where we wanted to have, if we wanted router 1 to be able to use this route and this route at the same time, for whatever reason, in order to do that, we can manipulate the variance command. And so in order to do that, we would just have to go into our Eigrp configuration. And configure it in here. Now, before I enter that command, I would like to explain what it's going to do. So, in order for a route to be inserted into the routing table, you can have, by default, equal cost paths will be inserted into the routing table. So, for example, this particular entry here in the topology table for 10.0.0.3, the metric or the composite metric match for both of these routes. So to get from here to here to router 3 is the same from here to here. So by default, because the metrics are the same, it's going to insert both of those entries into the routing table. So that's what we consider equal cost multipath. But if we want to have unequal paths inserted into the routing table, we have to use the variance command. So this particular path here to router 5 has one metric, and this particular path to router 5 here has a different metric. They're not the same, and we can see that by looking at the topology table, that through gigabit 01 it's one metric, one feasible distance, and through gigabit 00 is a different distance. So this particular value is lower than this value. So in order to allow this value to be inserted into the routing table, we need to update Eigrp and say if anything that's this value times the variance is allowed to get inserted into the routing table, because for right now the default value is 1. So anything times 1, it's its own value. But if we say this value times 2, now it's going to be higher than this, and then it's going to allow it to get inserted into the routing table. So let's do that really quick. We'll do variance times 2. So if we do show IP protocols, we will see that the metric variance value is now 2. And so if we go and run our routing protocol or IP route command here, show IP route, see initially we only had 1, but now because we updated the variance to 2, which means multiply this number times 2, and if this value is lower than this value times 2, then it qualifies to go into the routing table. So now we can see that we have 2 routes here. So now the router will send traffic this direction, and will also send traffic this direction to get to loopback 5. I really hope this training session was very helpful for you, and I hope that this can help you in your studies. If you like this training session, please leave a comment. If you have any questions, please leave your questions in the comments, and I will try to reply to them as soon as possible. If you like this video, hit the like button and also subscribe so that you can get notified when I post my next session. Thank you for joining.